have many constraints on we have many constraints. And this is the mass of the primordial black hole, and this is the abundances. We have many astrophysical and cosmological constraints on how many primordial black holes you can have in the early universe. And this one, you can translate this constraint into this bar. That's why we cannot go beyond it. If go beyond, you will violate those astrophysical constraints. But interestingly, even if you touch it, it will give you enough primordial black hole to be the dark matter candidate. So this is one of the interesting things about the primordial black hole. Okay. And this one, okay, you mean you give me a toy model. Can you really visualize in some, for example, the string theory? Yeah, we try to visualize the toy model in the axion holography inflation. Yeah, and a student is doing it. And another interesting thing is, so you produce a huge delta rho, and you may think about, you may also produce a lot of primordial gravitational wave associated with this primordial black hole. Yes, you're right, it is. This is the equation for the gravitational wave, and this is the photon produced during inflation. This is a source term for the gravitational wave. Yeah. And remember, we have we need to produce a lot of photon to back react to the inflaton to have delta rho over rho. And at the same time, this photon also source gravitational wave, and this is the equation for that. And how much gravitational you will produce associated with the production of primordial black hole is this, is the Bulan. And this one is the current pulsar timing away to search for gravitational wave. They didn't see anything, they put an upper limit. And this is the future sensitivity by SKA. And you can see, and this one is really within the frequency range of the PDA experiments, but it's still a 10 order of magnitude below the current sensitivity. But in the future, SKA and will probe this gravitational wave. This is another interesting thing to look at in the future. Okay, and back to Pei-Ming's question. We can create a lot of toy models to produce really supermassive black hole, and we just mentioned it in astrophysics, really difficult to produce such a heavy. Yeah, but inflation is just like a pizza. You order it, we just deliver in 20 minutes. The student can do it in 20 minutes. Yeah, you can produce 10 million primordial black hole as small as 10 devices, and then whatever you want. Yeah. And this is the this is quite just a few months ago, several groups, including us, look at the same problem. And different model, if give you a primordial black hole, just don't look at it. For example, primordial like this. And this is the gravitational wave associated with the production of primordial black hole with different masses. And it will give you gravitational wave at different frequency. For example, in this model, they can produce gravitational wave sensitive to LISA. And this one, again, sensitive to the PDA observation. And we can also produce gravitational wave associated with the production of primordial black holes with gravitational wave peak sensitive to advanced light. So this is the status of the development in this field. And okay, just forget. So we have finished the primordial black hole and axion. We have looked at the axion and also the primordial black hole. So how about cosmic violation. In this model, only one hand of the photon get pushed. And with this handedness, and the gravitational wave also have handedness. Yeah. And in the future, of course, it's very far future, and the gravitational wave detector could distinguish the two different kind of polarization of the gravitational wave, and they can really test this model. Check Axion infinity model. So this is why I advertise in my title the cosmic parity violation. In this model, there's a parity because Axion evaluate the CP, evaluate parity, and what's the signal? The signal is in this particular example. The signal is we have polarized gravitational wave. So you can tell in the future in gravitational wave measurement. And actually, I can stop here. If you're interested, as in my title is Axions with S. So inflaton is only Axion, no S. If you are interested and you have time, we still have time sometime, we can look at more Axions. And the Axion I also related to Chen Jihong recent work on the Axion dark matter. It could not be Axion. I mean, Chen Jihong 老师 the light scalar. It doesn't need to be Axion, but Axion is really well motivated light particle because they have protected by symmetry. Yeah. So, and this is now we talk about Axion like dark energy and Axion like cold dark matter. And actually, we researched literature a long time ago. Professor Liu Weidao, he already proposed to do scalar in order to have a complete general theory. I don't understand, even though I read so many times his paper, PLL, that many years ago. And the good news is we have at least one fundamental scalar, the Higgs boson, we have found it already. And the good thing about Axion is in string theory, the Axion holotropy, it realized the last field inflation. And we have heard about PQ symmetry to solve the CP problem, the QCD Axion. And this is about Chen Jihong 老师 use the 10 to the minus 22 eV scalar, and it's called the fuzzy cold dark matter. And Chen Jihong 老师 called the wave cold dark matter. It can solve many small scale structures problem. I don't have time to mention this one. And I believe the Chen Jihong group will talk about this a lot here. And at the end, I would like to introduce you a very funny word, Axions, string Axions. In string theory, there's a lot of U1 dimension, the last topic. A lot of U1 global symmetry, and associated with Axion. And it could be, the Axion could be very light, 10 to 33 eV, and up to 10 to minus 10 eV, including this fuzzy cold dark matter candidate, 10 to minus 22. It's about the middle. And later on, this work is about 2010, and it's already 7 years. And after this work, it's about a group of Stanford people. And luckily, I was there when I was taking sabbatical. That's why I learned it. Axions. Yeah, what a beautiful word, Axions. Yeah. And somebody generalized this Axions to include Axions as dark energy. And to have dark energy, the mass have to be 10 to the minus 40. Yeah. In this range, not yet. If Axion should be candidate for dark energy, it's lighter than 10 to the minus 33, about 40. So anyway, we have a complete spectrum of Axion mass to give you inflaton, to give you dark energy, and to give you polar matter. And that's the title, Axions. And what is it related to cosmic parity violation? Again, we are doing this Chern-Simons term. And think about this phi is not infinite anymore. It's finished. The first topic finished already. This phi is either dark energy or dark matter. And with this Chern-Simons term, just go back to Jackson's book, and you derive the Maxwell equation. And what is the photon optical index, or the photon dispersion relation? And this is the energy of the photon. And you have with this Chern-Simons coupling, you have extra term, minus plus. For right hand, you got minus. For left hand, you got plus. And it's related to the time derivative and also the gradient of this dark energy field or the dark matter field. And what's about this? With this optical index for both different hands, you will produce a rotation. If the photon is polarized, it will turn the polarization plane of the photon. And what's the speed? The speed is given by the difference of these two optical index, the right hand and left hand. And the omega is the speed of the rotation. And just modify. So now you will guess I'm talking about CMB now. Yeah. And with this additional propagation of photon, additional turn to the propagation of photon, and what we have done is to modify the CMB fast code. You can skip that one. Just look at this result. And this is the CMB photon coming from the last scattering surface at redshift 1000. It's propagating from all the way very far from us to our detector. And we know that CMB has a linear polarization. And it's propagating through the dark energy or dark matter. If this is represent the dark energy or dark matter, coupled to photon with a coupling string beta, and this medium will turn the plane of polarization. And this is this is also a campus for CMB. A lot of CMB people here, and I think it's gone too much. Maybe. Okay, this is the L. I suppose you have seen this already. This is the L, and this is the CL. The power of the polarization. And in the standard model, the standard Big Bang model, we have EMO. We have seen this already, the EMO. But we haven't seen the BMO. We haven't seen the BMO. We have seen the EMO of the CMB. And we will come to the data later on. We have seen it, the EMO polarization. And what is EMO polarization? Is the pattern of the polarization vector like an electric field. That's why we call it EMO. So in this CMB sky, if you measure the CMB polarization at every point, you will see the polarization vector, and some part of it will look like the electric field. Yeah. This is what we are seeing now. If the dark energy or dark matter coupled to the photon, it will change the orientation of the polarization vector. And it will change EMO into some magnetite-like pattern. And this is called BMO. In this model, with a coupling, non-zero coupling, this is a coupling, how big we need to realize the, to produce BMO is you just need to put a small number. And you can produce, you will convert some of the non-EMO polarization into BMO polarization. And this is example. For example, please look at this blue dashed line with a beta 10 to the -4, the coupling strength. We can convert the lone EMO into BMO. And Why I pick the blue line? Because look at this black dash line, this lensing. We call this lensing BMO. What's lensing BMO? Lensing BMO is we have a large scale structure in the universe, and the large scale structure is some potential well, and it will bend the light. It will bend the light, and also change the direction of the polarization. So the large scale structure can also convert some BMO into BMO, and this is called lensing BMO. Yeah, and we have seen this already. Let's look at the data now. Yeah, this is the effort human have put in searching the BMO. Do I have a measurement of the BMO? No, sorry. I should put it. No, sorry. I should let you see the BMO first. The EMO have been measured very well. Not very well, I mean, relatively well. It's really trace this curve. The EMO is, we have a very good measurement on this EMO. Yeah. The EMO, what's the origin of the EMO is induced by the Compton scattering of this Darren-Wolfer. And we haven't detected any, oh yeah, we do. And this is the observation. The bicep value, bicep data, and also the polar bear data. Yeah, they measure the BMO. And before that, there's a lot of experiment trying to catch the BMO, but it's only upper limit, and come with and also a group in Berkeley, the polar bear, to measure this primordial, this BMO. And this is the current status of the measurement of the BMO, the bicep data, and the polar bear, and also the SPT, the South Pole Telescope, and also another this is in Chile. So this is the current state of measurement. We confident that there's a detection, but you can see there's a huge error. And now the next generation CMB project, including the NTU effort, they're trying to measure the BMO at usually this length scale, not this small length scale. The bicep instrument. And so let's go back to some history. And bicep, they saw gravitational wave induced BMO, but not yet. You see the dust. This is a dust fog. This is a dust fog. And now everybody knows and also convinced the bicep measurement is about the dust BMO, not really the gravitational wave induced BMO. And also this is the lensing BMO, the conversion of the original EMO into BMO by the gravitational lensing of the large scale structure. And this is the current status. And what we are talking about is the dark energy and dark matter induce BMO, and we usually call this a cosmic birefringence BMO. What's birefringence? Birefringence means the optical index for the right hand and left hand are different, and that's what the toy model gives you. And it can, in this model, it can produce BMO. And for example, we have seen with the beta 10 to minus 4, it gives you a BMO. And this is with what? If the dark energy amplitude is A, and beta square, the product of this parameter space around this number is still allowed. This number is still allowed in all observational astrophysical constraint. Yeah. And we have some positive detection of the CB mode. And this is from the dark energy. And this is from dark matter. If the dark matter is 10 to the minus 22 eV, fuzzy cold dark matter, and you believe it's axion, and axion have perturbation, delta over rho, and it related to delta phi over phi, and remember the delta phi, the time derivative, and also the spatial derivative will give you different optical index for the both end of the photon, and it will rotate the polarization vector and convert E mode to B mode. And this is example. And we have seen the dust B mode and the Lansing B mode. We can produce a CB because it's Birefringence B mode, something like this. Yeah. In the future, in the next generation B mode experiment is very interesting. Yeah, we predict some excess B mode around L2000. Yeah, and we have asked the CMB people to look at this possible signal. And this parameter space still allowed subject all constraints. And this is what something around this. Anyway, the last page can show. Okay, I'm done here. Yeah.
Well, let's end the speaker. Then, do you have any questions?
So when you say that the black holes could be candidates of the cold dark matter,
Yes.
is it possible that all of the cold dark matter are black holes, or only account for part?
It's possible. It's possible. Yeah. Although we have seen there's many constraints on the primordial belt spectrum, but one particular yellow spectrum may not be enough for the cold dark matter. But you have a broad spectrum, then yeah, we have enough. Yeah, primordial belt could be enough for dark matter to melt the dark matter.
Another question: if axions are coupled to photons, why haven't we seen it?
Oh, you mean? Good question. Yeah, we are in experiment. Yeah, but it's a different regime. Yeah, now there's a lot of constraint on photon coupled to axion, but not on this mass range.
Oh.
For example, MEV axion. Yeah. And
That light.
I've mentioned many times. All the models still survive subject to all the experimental constraints and astrophysical constraints. Yeah, there's a lot of constraints on action. Yeah.
Oh, I see. Actually, my question was, is since we didn't see axions, there should be a lot of constraints already. So now in the early slides that you have so many parameters, tuned parameters, which can give you these primordial black holes during the inflation, right?
Yeah.
So actually, there's no experimental result actually violate, or so this set aside all the constraints already. That means we have a lot to do.
Yeah, sure, yeah.
Okay. Any other questions? Okay, this is actually the new field to us. I mean, new compared to these high students. I think this students, maybe that there will be a lot of work in the future. You may consider at one time you can join this kind of research. Okay, this is really a new things. All right, thank you.
Yeah,
Let's thank the
thank you.
speaker again.